Hello everyone. Good evening. Am I audible? Can anybody confirm? Hello Hers. Hello Kajal. So just somebody can please confirm, like you can type or through the message or something. Am I audible? Hello.
Yes, sir, you're audible.
Thank you. Thank you. So this is the first live session for the course and introduction to cardiovascular fluid mechanics. So I will be projecting my screen. Uh, Wait. So this, I hope the screen is visible. Let's fix it. So mostly the sessions that in this particular session, whatever assignments are being floated for weekly assignments. So this session will be somewhat recap of whatever has been taught throughout the week, and at the same time, there will be some discussions on some of the key concepts that sir has taught, or maybe sir has just skipped it a bit and left it to do the calculations and everything from your side. And also we will be solving some problems related to the stuff that has been taught in the entire week. The questions will be a bit difficult as compared to the assignments that has been provided for week one, so that the assignment seems to be easy for whomsoever who is solving the assignments. So I will be just starting. So like anybody just so you all are from chemical engineering, or like what is the background? So you can just type or just say, unmute yourself and tell. So I want this session to be interactive, like you can ask something, then at the same time I will be trying to answer as much as possible. So like hers, so you are from which background? Like fluid mechanics is there, so maybe mm. So like in the first week, mostly an introduction was there, and at the same time, just after the introduction, like some basic fluid mechanics review and then solid mechanics review was there, because these two concepts will be used, and uh, they, they will be coming up in various related uh, stuffs. So like uh,
Um, sir,
yes, yes, speak.
sir, I was not able to access the introductory session. This
Okay.
is Pratiksha here.
Yes, yes.
Uh, how can I access it, sir? And can I access it?
No, like the course week one lectures you are not able to access.
No.
Oh, actually, there is this. I will be showing you this Swayam portal is there.
Swayam portal, yes.
Yes, from there you can access now the stuffs. Wait, I am telling this. Wait, let me just open something, some other stuff. Wait. So, so from the Swayam, what you are not able to access? Hello.
Sir, the introductory session you mentioned about?
No, introductory sessions and everything that is being taken by instructor. That is Raghavendra sir. And then for each week there will be some live sessions. So that live sessions is being taken by a team member. So like for example, for this particular course, I am the team member, and similarly for other courses there are different team members. So uh, like you just have to go for Swayam. I will be just opening the website. Yes, here. For example, So similarly, like you are having login, you will just go to the course Introduction to Cardiovascular Fluid Mechanics, right? And then, uh, so like in this one, these are some of the, for week one, there was week zero assignment, and then there is just lecture one, two, three. I hope you have gone through these lectures, right?
Yes, sir.
After that, there is this live session. This is first live session. And then there will be week two assignments coming up, and then there will be another live session. For each week, there will be one live sessions, and at the end also there will be one extra live session where the cumulative discussion of entire course will be done, right?
Okay, sir.
Okay, okay. So,
Thank you, sir.
okay, welcome. So that was it for this. And thing is, here I will be actually putting some of the questions related to the content that sir has taught, and I will give some time for you to answer it. You can just type it on message, and then we will have discussion on the same. And in the questions that is there in first week assignment also, you can, if you are having some doubt, that you can ask, or some doubts that you are having after watching first week of the course, that can also be discussed here. So, like, question one is, what is the assumptions for, what are the assumptions for assumptions for wait, somebody came, let me join them. So admit all. Yes. Assumption for Hagen-Parsons equation. So maybe Hagen-Parsons you have gone through equation. Okay. This is uh, and the options are, option A is valid for laminar flow. For laminar flow, B option is, uh, here the pressure drop is directly proportional to volumetric flow raised to the power 2. Option C is uh, valid for fully developed flow. Option D is, it's independent of viscosity. Like delta P is in pressure drop is independent of viscosity. You just attempt it. So two, more than one option could be, can be correct here. So you go through this and just, you can type also, or admit all. Yes. So I will be taking, like, mostly second lecture and third lecture, I will be having some more questions. So because most of the questions that are there for the week zero and one first week, mostly first lecture questions has already been taken into the consideration. And mostly in the final exams, this type of questions will be asked, which will be there somewhere in the slide or in the discussion, or maybe instructor or we are actually telling you to focus on. So, like, what are the assumptions for Hagen-Parsons equation? Uh, A is valid for laminar flow. Uh, its validity, not the assumption, its validity. Validity for eigenpossily. Validity for eigenpossily. And the pressure drop is directly proportional to volumetric flow rate to the power 2, valid for fully developed flow, and delta P is independent of viscosity. So when you actually look at the uh, Hagen-Pauli equation, then you will come to know that this delta P is 8 mu L, where the L is the lateral length, and let me just change the color. So delta P is equals to 8 mu L, 8 mu L divided by pi r to the power 4 multiplied by q. So from here we can see that, and again this is for this is valid for a pi flow, the way it has been derived. So you can the derivation for this is clearly explained in the basic fluid mechanics courses. So if you want me, I can just derive it once, but this particular course is something ahead of the basic fluid mechanics, where here you are actually considering the wall effect, because whatever flow which is happening in our body, in our veins, in our arteries, uh, the wall which is there, those are not rigid, they are flexible. So there will be somewhere, there will be contraction, and there will be elongation of the vessel, and because of that there will be and at the same time the blood pumping happens at the heart. So because of that, the flow is a bit pulsatile, it's not like uniform flow. So because of those reason, this particular equation will not be directly valid to the condition in the vascular system. But yes, this has to be considered, and this is very basic equation which actually tells us how the the volumetric flow rate or the flow is relating to the delta P, which is pressure drop. So this is valid for fully developed flow, this is valid for laminar flow, and this one is wrong. And then delta P is independent of viscosity. No, delta P is depending on the viscosity. So this is viscosity. So this is also wrong. So A and C is correct answer. So now we will be taking another question, like question 2, and I have already compiled all the questions, so I will be just putting it there. So like uh, the 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 phenomena involved in human body can be considered uh, in terms of considered in terms of transport phenomena. So what are those those processes which are happening in our body. And uh, like we know that this transport phenomena, this is a bit general question, like transport phenomena that we usually study. This transport phenomena, it involves transport of momentum, that actually comes under this fluid mechanics, fluid flow, fluid flow. And then there is this transfer of heat heat transfer. This transfer of heat is what, uh, this is important for the vascular system. uh, like in the lecture also, sir has discussed somewhere this, uh, this blood flow of the blood is important in order to maintain the body at a constant temperature. And at the same time, there is this uh, nutrition transport throughout the body through the blood. So it means this, there is also mass transfer, because this transport of nutrition is another kind of transport phenomena. So this transport of, this is like flow of blood, uh, fluid flow, like blood flow. In our case, in the context of this course, heat transfer, the maintaining body at a constant temperature, and then again the mass transfer, transport of the nutrients, and then again this transport of the hormone is also done by this blood. So these are the three things that is actually this, in within our human body can be considered in terms of transport phenomena. The next question that I want you to solve is, so if in between, if somebody knows answer, you can just type below, because like there are so many stuffs. So I will be giving sometimes. If you want to discuss, you can just message in the message box. We will be discussing. So next is like, what is the uh, some stuffs that like there in the course there has been three type of moduluses that has been taught. Question three. So this is a bit clear question, straight questions. Like first one is bulk modulus. So uh, first was modulus of elasticity. Modulus of elasticity. Then there is this bulk modulus, and then there is shear modulus. What are these? Like, can somebody define it, or what is the expressions for these, and why these moduluses are important, or and why this fluid dynamics is of course important for this particular course? Why this solid mechanics is also important for this course, to study them? Shear modulus, bulk modulus, and modulus of elasticity. So, so these three modulus. Yes, somebody just wrote some. Yes, web. Oh, yes. अच्छा, web. Mm, so at the very beginning, where this elastic uh, solid mechanics started, there first you have been taught about this shear stress, that it is the force per unit area, uh, and then this strain is nothing but when a rod is being elongated, there is change in length from the initial length. So this that change divided by the initial configuration is the strain. And when you take the ratio of stress and strain, then you get first modulus, which is this elastic modulus. So this elastic modulus is the ratio of shear stress to the shear strain to strain. So this the slope for the curve sigma to strain. Uh, Obviously, this curve itself is versatile in terms of if you are dealing with the something brittle or something ductile. So there will be differences. For that also we are having one question. But this first modulus that you have encountered is E is sigma by epsilon. The physical significance of this is this moduli gives you the rate of change of shear stress to the rate of change of shear, the slope. So there is something called instantaneous moduli that is for the abrupt change of some solid uh, deformation. And another one, the modulus that has been taught about during the discussion was the bulk modulus, and that was again this bulk modulus is what? Anybody? Anybody? Bulk modulus. So elastic modulus is clear. So it's sigma divided by epsilon, and then this uh, incremental elastic modulus that you have already discussed in the class is d sigma by de. That is nothing but the slope of shear stress to the strain curve, and this slope actually defines like whether there is the rupture point, breakable point, or at in what regime the stress bearability of the solid is. So this so bulk modulus is the another thing that we were discussing is this uh, bulk modulus is mm, there you have had the final expression. This derivation is there is E. This was the elastic modulus divided by 1 minus 2 nu. Okay, so this bulk modulus is there the unit dimension has been considered, and this overall stress to the strain relationship was considered for this. So this if you will be actually looking at the exact significance of this one, let me just someone want to join the call. It's like people are coming at different time instances. So let me just take that. Yes, he came. Okay, so this bulk modulus is a measure of material's resistance to uniform compression. Okay, and this is defined for incompressible. It defines how incompressible a material uh, uh, is when it is subjected to the pressure. So sometimes this bulk modulus is defined in terms of pressure also. So people go for this. Uh, so this is an empirical relation that we got, but this exact k equals to delta p divided by minus delta v by v. So and more generic relation is this uh, delta p divided by minus of delta v by v. So it's the volumetric strain, and here is the volumetric stress. So this is volumetric stress divided by volumetric strain, and this is another thing, and uh, this bulk modulus will be related to some other moduli, which is our isotropic elastic modulus. This is capital is the isotropic elastic modulus, and nu is what this has also been explained in the class. This is the Poisson's ratio. Like Poisson's ratio for Poisson's ratio, and this one is elastic isotropic elastic modulus. So you see this uh, the relationship of this. So what is the relevance of this in biomechanics? Like this one is the biomechanics where the fluid dynamic uh, movement, like blood flow within the vascular system, where the boundaries are flexible and they are also deformable, and somewhere there will be bifurcation, there will be change in uh, flow patterns because of change in the cross sectional area, because when you are going from the artery to arteriole and again towards the capillary, then there is like very abrupt change in this diameter of the blood vessel. And also sometimes based on your breathing pattern, there will be change in effective internal diameter of the blood vessel, and that also leads to change in this elastic modulus, and that gradually can be reflected in terms of change in this different bulk moduli. And so this in biological tissues like arteries, this bulk modulus indicates how much the tissue resistance or the volumetric deformation under pressure. So what is the volumetric deformation under pressure? And it contribute to understanding of the stiffness of the tissue. So another question is like this can be thought of is uh, uh, physical physical.
Uh, Hi, I have a question,
Yes, yes. Hello.
right? So if the Poisson ratio is 0.5, in this case, the bulk
Yes,
modulus will become infinity, right?
yes.
Is that possible?
So the Poisson ratio, the way it has been derived, once we look at the derivation of this, let me just see in the lecture. So in that case, this that what we think is the bulk modulus will go towards the infinity. Means that the material resistance to any volumetric change, that will be consistent with the incompressibility, right? So like for example, this I will go through once. I will be taking it in next lecture. Okay. So hers, you are asking, right?
Okay.
So definitely in
Yeah,
the
yeah.
next lecture I will be taking. Even I haven't actually looked at it exactly. I will be
Okay.
definitely taking it in uh, with the clear examples and explanation. So good
Okay.
question. So this one, like this particular definition of the bulk modulus doesn't involve this exact 0.5 factor. So this is coming when we are relating it to the moduli. Okay, I will look at it. Right. So now the another question that is there is what is the physical significance of bulk modulus? So anybody just point it out. you can type also. Hello, anybody just type physical significance of bulk modulus. So like here only I have said there is this volumetric stress to the volumetric strain, and also this can be explained in terms of like how this bulk modulus is relevant to the cardiovascular fluid mechanics. So so actually this bulk modulus explains us like materials resistance to uniform compression. So materials resistance to uniform compression. Okay, and then again from this also we can see like how materials volume changes under applied pressure, providing a insight into its compressibility and incompressibility. So like the change in applied pressure will lead to different changes in the volume strain, volumetric strain. So resistance to the volume change means like when the K is high K indicates that a material that is harder to compress, means it is more incompressible, like metal or liquid. So metals and liquids, they will be having metals or liquid, they will be having high K value, which is bulk modulus, and at the same time K will be lower for gases, obviously, uh, because in that case they will be compressible. Okay, so in our for in context of this course, this this particular factor is important in order to understand the stiffness of tissues. Stiffness of tissues, because these arteries and veins are nothing but tissues. So stiffness of tissues, stiffness of tissues, or uh, uh, blood vessels, we can say blood vessels. Uh, Now, the next question that we are having is this related to the next topic is this, where is that? Yes. Hmm. What is transmural pressure? What is transmural pressure? Anybody? What is transmural pressure? What is transmural pressure? So this transmural pressure is uh, the difference between the inside and outside pressure of our blood vessel. So this, if you say delta P, which is this transmural pressure, this is defined as, so there will be one pressure inside the vessel, which is obviously because of the flow and in this blood flow, and then outside the vein, or there will be uh, P2. So this difference is this one between inside and outside pressure. Inside and outside pressure. Okay, and this delta P is uh, responsible for uh, hoop stress. So, like in the section of thin walled cylindrical tube, where this thin walled cylindrical tube has been taught, in this elastic, this solid mechanics section, because two assumptions could be taken. This thin walled cylindrical tube for one reason, and then somewhere there is thick wall consideration. Uh, Mostly thin wall consideration is valid, uh, and this P is leading to hoop stress. So there is two stresses coming up into the picture as we are solving it in the cylindrical coordinate during the discussions. So this hoop stress, when there will be this force balance on a part of the tube, this pressure difference causes stress. Then this transmural pressure is also difference in the pressure across the wall of the hollow structure. For example, sometimes this is defined in different terms. Like for the blood vessel, also it has been defined. it could be defined for this heart chamber also. It can also be defined for the lung chamber. And so it is nothing but the pressure inside minus pressure outside. So this transmural pressure uh, is tells us about the inflation and collapse. So if a positive transmural pressure is there, for example, this Tm is positive, indicates that the pressure inside exceeds the outside pressure and causing the structure to inflate or stay open. And if this is negative, there will be the collapse. If the walls cannot resist the pressure difference, there will be this uh, uh, like kind of evacuation kind of thing will be happening. The wall will be getting collapsed. So the this the physiological application of this transmural pressure is this blood vessels, lungs, and heart chamber. So where there it is being applied. So transmural pressure is a vital concept in physiology, and this in biomechanics, and they provide the insight into the mechanical behavior of the and the function of the hollow structure. Next question is like uh, here, if we say here is that the one delta p1 is this one. So like uh, here the question that has asked is if this nu is half, right? Then what will happen? The denominator will become 0. So then 1 minus 2 nu will become 0. And then k will be going towards the infinite. Okay. So if k goes towards infinite, then yes, k goes towards infinite means volumetric stress to the volumetric strain is going towards infinite. It means volumetric strain is becoming 0. It means this part is becoming 0, right? You are there, Hers. Okay. So this delta V by V becomes 0. And this delta V by V becoming 0 implies that there is no change in volume. Almost there is no change in volume. So this is not finite. Not finite. It means the solid for which this bulk modulus is being calculated is an incompressible solid. So the we can interpret that solid is incompressible. Okay. So the solid is incompressible, and at the same time this k suits up and k goes towards infinite means k is very high. So this particular answer could be interpreted that if this Poisson ratio is half, then uh, this the material is considered to be perfectly incompressible. It is not compressible at all, and there is no volume change like this equation also says. But this 1 minus 2 nu, and when we see it in terms of definition of nu, the definition of nu is, as you remember, this nu is the Poisson ratio, and the way Poisson ratio we have defined is this strain in strain in transfer direction, like ey to ex and ez to ex. So if this is going to be half, it means what? The ratio of strains are half, right? And also the ratio of strains are half, and at the same time, like when you compare it with the z and with the x also, so this this actually defines that this perfect incompressible solid, perfectly incompressible material, there will be no change and there will be no deformation in one direction. Like any deformation in one direction is entirely compensated by deformation in the perpendicular direction, right? So whatever deformation is happening in one direction, so we expect that because of that deformation there will be increase in volume. Okay, so so another direction will have somewhat similar deformation, but it will try to decrease the volume. So net there will be no effect in terms of volume change. So like this for isotropic materials, as we had this E, this is elastic moduli, and this elastic moduli is related to this bulk moduli like this. And when this is 0, this is zero point 0.5, and this becomes 0, this reflects the material's resistance to any volume change, and it says that consistently the material is incompressible in nature. So if the in fluid dynamics, also in fluid dynamics, incompressible fluids are assumed to have this Poisson ratio value 0.5, and they they do not possess shear resistance as solids do, right? So similarly, for materials like rubber or biological tissues, under certain condition, uh, this uh, uh, this new value is assumed to be 0.5, and numerically also this value is assumed nearby 0.5, like 0.4 or 9 or something, in order to have stable numerical solution. So the next problem, this was the question that he asked. That time I was unable to tell this. Next one is the questions about stresses, like the hoop stress, and then thin walled consideration, approximation. Those are important as per the final exams. So that has to be read thoroughly. Okay, so which of the statement, what is true, what is correct as per thin walled cylindrical tube? Thin walled cylindrical tube. Okay. What is correct as per thin walled cylindrical tube? The A option is force developed in the wall are tangential to the in the wall are tangential to tube surface. B option is force developed in the wall are normal to the tube surface. C option is measure blood vessels can be considered as thin walled. Okay, thin walled elastic tube. And D option is in case of SC symmetric geometry, there is no shear force and only normal force exists. Okay, in the axial and the circumferential direction. In axial and circumferential direction. Okay, so like in case of axisymmetric geometry, so if you consider the axisymmetric geometry for this particular thin walled cylindrical tube, then only this uh, normal force exists in axial direction and circumferential direction, and not the shear force along the axial direction, right? So which of the following is correct as per the thin walled cylindrical tube? This is not there. So, somebody is Prem Pratiksha. So if you actually go through the question, then this was clearly explained in the lectures. So A is correct, right? This is multiple correct options. So you like there can be three or two options can be correct. A is correct, right? A is correct answer. Hers difference in the pressure between inside and outside vessel. Yes, Harish, that was right for the transmural. And Harish asked that question, right? Harish, like what I expect is this for incompressible solids will be the situation when this nu is half, which is this Poisson's ratio. Harish is there or not? No, he is not there. Right. Okay, we'll watch the videos. Anyway, these videos are recorded, so they will be there within the same list at the this Swayam portal. So the next question, you solve this question. A is correct, right? Any other options? Anybody can guess. Till then, I am writing the next question. You just keep thinking about the same. Uh, and so this uh, just attempt A, B, C, D so that I can move. So in this one, if you see this particular one is correct, and mostly this consideration is made that this thin walled cylindrical tube, most of the vessels in our body can be considered in this limit. And thin walled cylindrical tube means thickness to the radius. So thickness is 10% or below 10% of the radius. So and in case of asymmetric geometry, there is no shear force and only normal forces existing. So these generalization have been made based on the overall effect that is prevalent based on the phenomena that is happening. So if a particular blood vessel is being analyzed based on its radius to the thickness ratio, they got to know that this below the thickness is below 10% of the radius, and then this particular uh, effect, they observe that in that scenario the deformation of the walls of the blood vessels are more. So for example, if this is the blood vessel and the thickness of this, if you this blue colored line, if the thickness of this particular thing is t and the radius of this vessel is r, then thickness to r should be less than 0.1. Okay, so in that case, they observe that this particular vessel is having uh, very high lateral fluctuation. Lateral fluctuation means the wall of this particular vessel is having lots of undulations. These undulations, these undulations are causing the deformation of the wall of the blood vessels, and because of that, there is the change in the flow pattern within the blood vessel. So now it becomes very important in order to have this the pressure drop to the flow velocity, like pressure drops relationship with some flow variable, for example volumetric flow rate or the velocity of the fluid which is flowing inside or the velocity of the blood. So this hematodynamics, the knowledge of the flow and the pressure drop within this complex vessel becomes important. And so if they consider the asymmetric geometry of this particular blood cross section blood vessel, and they observe that the only normal forces, because of that, because of which these formations are happening, it exists in axial and the circumferential direction. So in the axial direction also there is some kind of deformation. So and in circumferential there is this squeezing and bending happening. So this is anyway three-dimensional. We are only able to look at the 2D aspects of it, but will be three-dimensional in nature. So now the next question is related to this hoop stress. So the question says, uh, what is physical significance of hoop stress in context of blood vessels, right? And what will happen to the hoop stress if uh, A is A is wall of the blood vessel is thick, another one is wall of the blood vessel is thin, vessel is thin, right, thinner than A. Okay, so in which case the value of hoop stress, like the order of magnitude of hoop stress, where it will be high or low. That is the second part of the question. And the first part of the question says is, what is the physical significance of hoop stress? Like, you understand that the blood is flowing through the blood vessel, and then inside the blood there is this 46% this uh, we know this RBC is there, 1% is the WBC and the platelets, and rest 56% is about this food, 54% is about the plasma, which is somewhat more Newtonian like constituent of the blood vessel. But the thing is, whatever fluctuation and the deformation of the boundaries of the blood vessel is happening uh, because of again the because of this ratio of the thickness of the blood vessels to the radius of the blood vessel. uh, there is this development of the different stresses at different locations. So hoop stress is again it's more like solid deformation stuff. So this is stress within the solid, not of that of the fluid. So any shear or any stress within the fluid, that is the another thing, that is the tau that we will be discussing. But within the solid, this hoop stress generate at the circumferential level. So this hoop stress, what is its physical significance in our blood vessel? So you can type also, or anybody can unmute and speak. That will be great to have one to one question answer. Anybody? Like Harik is there. Hero Kalita is there. Okay. So this hoop stress, and then what are the this is a bit comparative. This kind of comparative questions can be there in the final exams also. So like there will be some order of comparison of different parameters that are being derived within the course, or like that are being told to you. So always sometimes there will be option there in the final exams. There will be some of the questions which will be more generic ones, somewhat integer type questions, or somewhere some logical explanations will be required, match the column kind of thing. Not always the MCQ type, or sometimes it will be multiple type questions. So like the logical understanding of the things, the trend, the dependency of one parameter to another is important. So you just think about this particular question, like hoop stress. So this is also known as this circumferential stress, like explained in the lectures. So again, it is a mechanical quantity, like we have discussed. It's like more of coming from the elastic solid uh, definition. So hoop stress, also known as the circumferential stress, is a critical mechanical quantity in the vascular system, right? It represents the tensile stress acting tangentially along the circular cross section of the blood vessel. So its tensile stress. Okay, its tensile stress acting circumferentially circumferentially, or like we can write it in more easy form, tangentially, right? Tangentially along along the circular cross section. Along this circular cross section, right? So that is one thing. Another thing is the this why this hoop stress is important in vascular system is it actually maintains the structural integrity. It maintains the structural integrity, right? So like we saw that this hoop stress, like we had in the discussions, कि this when you consider this blood vessel, the radial part of the half the blood vessel, and this was the R, and this side you had these stresses coming up into the picture that we called as hoop stress. Okay, so this was this thickness of the blood vessel again, T, and obviously this blood vessel will be elongated in the, like it will be having some length. So if you consider that length to be dz, right, and this you have considered to be x and y axis, and dz is the another dimension which is giving the length of this. So there you have defined that this particular area will be the one projected area where this hoop stress the hoop stress will be acting at these circumferences. So like there will be this force balance in x direction. So force balance in x direction. Okay. So this will give this. Obviously, this intramural pressure will be P inside. So you will have P, which is pressure inside minus outside. That is the difference, and this is acting for that projected area, which is this 2r times dz. Okay, so 2r times dz. It will give you the one. This is two places where the balance is happening. So 2 sigma theta is the stress, and then this is acting for this particular circumferential periphery. So this is 2 t dz, right? Then after solving we will get 2 theta to be intramural pressure multiplied by r, transmural pressure multiplied by r divided by thickness. So from here we can see that when the thickness is high, when the blood vessel is thick, then sigma is high, sigma theta is high, and in this one sigma theta is low. Means low hoop stress will be generating for the thinner walled blood vessel, and high hoop stress will be generating for the thicker walled blood vessel, right? So now another question that is there is which is the correct match. Correct match. Okay, so which is the correct match for the following? Okay, so option A is like this hoop stress, that is sigma theta equals to PR divided by T, right? Sigma theta equals to PR divided by T. Okay, and this sigma theta divided by 2R PR divided by T. This is hoop step. So there will be this A and B will be this one. So there is this two columns, A, and then there is this B. So B is what? Circumferential stress, right? So in that there will be two. So open-ended, ended vessel, circumferential stress, right? Stress. What is this open-ended vessel circumferential stress? The expression for this is what? If it is B, so I will write PQR this side. PQ. Q is this sigma Z divided equals to PR divided by 2T, right? Okay, and then C is this close-ended vessel circumferential stress, which is sigma Z. This comes PQR. This is sigma Z equals to 0, right? So which of the following is correct? So clearly you get an idea that this for hoop stress we have already discussed anyway in the last question. So A is matching to the P, which is sigma theta equals to PR by T. That is hoop stress. Okay. And then this circumferential stress is the one that is there in the B and C. So again for the open-ended vessel circumferential stress and the close-ended vessel. The tip of the any blood vessel where afterwards there is no flow is the close-ended vessel. That is also called this that is this longitudinal or axial. This is a bit longitudinal or axial stress. This one, longitudinal or axial stress, and this one was the hoop stress. That is also called circumferential stress. So there is a bit this change. This is this sigma z. You write it sigma z. Sigma z. So this is B option is for the open-ended. So for the open-ended, as you understand, this open-ended, for the open-ended, there will be this 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 sigma z to be 0 for open-ended. So as there will be no delta, this as per the derivation, this B comes for this PQR R option, and this C comes for C is for Q option. So the derivation for the for all of these has been discussed in the class. So this was just for the revision of the same. So this similar problem can be there in the final exams. And also, what is the relation between this? For example, if I can just talk about if you are in the case of close-ended vessels. So for close-ended vessels, for close-ended vessels, right? So close-ended vessels, this P, so the balance that you will be getting, you can just look at this once in the lecture again. So the balance that came was this P pi r square into sigma z. That was this circumference one, because this is happening in this direction. Suppose this is the blood vessel, this is happening in this direction, right? So so the pressure is actually having this complete pi r square area in its font, and then this axial stress is generated in this direction opposite to this. So it is thus 2 pi r, and the thickness was t again. So 2 pi r was the resistance t. So this actually is the area for at least this sigma z is acting, and it gives sigma z to be pr divided by 2t, right? And when you actually compare it with the hoop stress again, so it comes out to be sigma theta by 2, means this axial stress is half of this hoop stress. Okay, axial stress is half of the hoop stress. And similarly, like when you see this for this one, if you calculate the radial strain, it comes out to be change in the radius divided by radius, right? So change in the radius, if there will be expansion or contraction, is what? That is delta r divided by r. Okay, and then there will be this azimuthal, this theta. We call it a hoop strain within e theta. That is actually the 2 pi initial radius of r and final radius was delta r change. So that minus initial this divided by 2 pi r. So you will get delta r by r. Again, they are same, right? They are same almost, epsilon r and epsilon theta. So this, when you see this epsilon theta, like you had initially from the definition of this elastic moduli, you know that E is sigma theta by sigma epsilon theta. So it gives that epsilon theta to be sigma theta divided by E, right? And sigma theta, this sigma theta is the calculation that you already did for hoop stress was PR by T divided by E. Again, E comes up, right? And this you have already calculated here to be delta R by R, right? Delta R by R. So this will give delta R, means change in the radius, to be PR square into moduli multiplied by thickness. So this is another aspect of what is the change in the radius because of the hoop stress. So that can be calculated for given the thickness and the moduli and the transmural pressure. What is the final radius for the particular cross section if you are looking at. So the now we will be actually moving towards this what is plane strain formulation. Okay, so in this one, like thick walled, thick walled cylindrical tube. Okay, this was considered during the discussions. So thick walled cylindrical tube. Okay, so if you we see, so in this one, suppose this is the question: what is thick walled cylindrical tubes, right? So we have seen that these thick walled cylindrical tubes are what? When this thickness to the radius is greater than 10% of the thickness is greater than 10% of the radius of the vessel. So suppose this was the vessel. Suppose this is the thickness of that vessel. This thickness is more than 10% of that radius. Okay. So sometimes thick walled formulation is also required, and and why this thick walled considerations are important is the very first understanding is this: the arterial wall. Okay, so there the restricted movement happens in the axial direction of the arterial wall, means the deformation in the axial direction is negligible for this arterial wall. Okay, so if we see this arterial wall, okay, so there is this restricted movement in this x direction, right? In axial direction, for example, it depends which direction you have taken to be axial. So in most of the derivation that sir did in the class, he was taking this z to be the direction towards the axis, right? And then this the here in this one they have considered this plane strain formulation for these type of systems. For example, what is this? If in the case of thick walled, as in the lectures we have mentioned that the thickness to the radius is an first definition, and then this is applicable for many cardiovascular applications. Okay, thick wall consideration. For example, the arterial walls are tethered, means the movement in the axial direction is restricted, right? Means they have considered this plane strain formulation. So what is this plane strain formulation? The point is, what is this plane strain formulation? So this, so it means restrictive movement in the axial direction means what? Like there is this along the axis effective zero. So strain is zero along the axis, right? Strain is zero. Strain is zero along the axis. Okay, and if the strain is zero along the axis, we can say that this if we actually consider this deformation in the 2D plane, so that is the one plane strain formulation where deformations are assumed to occur only in the radial and the circumferential direction. So deformation, okay, deformation only in radial means along the radius of the tube, and circumferential directions. Okay, means 2D plane we are considering, 2D plane, right? And the axial direction is constrained, means we are, this point actually tells us that epsilon z is zero. There is no strain in this particular direction. Epsilon z is zero, right? So stress in the axial direction means in this case strain is zero, but stress can exist, may exist, and that will be actually calculated based on this equilibrium condition, right? So that was the one thing about the thick walled cylindrical tubes. Uh, that is one of the assumptions for which this has been explained. So, so like which of the following is correct equilibrium condition for thick walled cylindrical tube? Okay, so I will be writing some of the equations. You need to just tell me which of the following option is correct. So about these concepts, there was very few questions in the assignment of the week one. So most of the questions that those are there in the assignment. If you are having any doubt, you can ask me here. So that is also one part of one important aspect of these lectures, these live sessions, so that you can have one-to-one interaction, and at the same time, I will be discussing what are untouched in those assignments, or some of the concepts that will help you in solving those assignments, right? So because mostly the deadline for those assignments are like uh, 10 days, I think, 1 week plus 3 or 4 weeks. So for the last assignment, you will get almost the next week as a deadline for submission. So there will be discussions like that. You are having almost 7 or 5 to 7 days to think about the same. So like uh, which is correct about about thick walled cylindrical tube, thick walled cylindrical tube, right? So option A is okay. So there is this 2D strain formulation that we have considered. So this is right here derivative of derivative of radial stress plus the difference between the circumferential stress circumferential and hoop stress divided by R summed together is equal to 0, right? It says that the option is says that you are having the derivative of this. So I will be giving some of the clues. B option is this del sigma. So this d sigma r divided by dr, okay, plus this sigma r minus sigma z divided by r equals to 0. Is this correct? C is sigma theta d divided by sigma theta plus sigma r minus sigma z divided by r equals to 0. And D option is d sigma r divided by dr plus sigma r minus sigma theta. These are stresses divided by r equals to 0. So which of the following is correct? So about the thick porcelain indicator. So more than two options can be correct. So that has to be taken into consideration. So Pratiksha is there, Prem is there. So you both registered for the course or just watching and learning? Like you all will be giving the exams. So
Yes, sir.
still I think time is there for the registration. It's good na, like only 4 week course is there. Sometimes like 4 to 8 week is good, but 12 week sometimes it takes longer time and longer patience. So almost
Yes, sir.
similar questions will be coming uh, in the final exams also. There will be mostly from the slides and the content that sir is explaining and whatever is being explained here. Only few questions will be there, somewhat related, but they will be somewhat different. But very few questions will be like very new to you. Almost every questions will be discussed either in the assignments or in the class or in the live sessions. So this is a bit package. So whatever live sessions like I am taking, it will be somewhat recap of whatever has been taught in the last 3 or 4 lectures, whatever is there in the entire week. So I am just having some questions from the first lecture and some question from the third lecture, and based on sometimes I am actually looking at whatever is there in the assignments, what new can be uh, be touched through the courses that I am taking in the live sessions. So that entire content can be compiled through the questions. So this you just attempt, Pratiksha or Prem. So these stresses and why these calculations are important. Anybody, Pratiksha or Prem? Why these calculations are important? Why we are actually calculating the stresses, then strain? We are actually looking at the blood vessels and it's just flow. And why this is important for this particular course? So, so you was knowing about this, like what all will be the content of the course before registering for the same.
Yes, sir.
So your background is Pratiksha, like the department.
Sir, I'm a first year RVC student of
Oh,
biotechnology.
so biotechnology, right? So in the biotechnology, mostly this fluid mechanics and these things are not being taught, right? Uh, that's why I think the basic fluid mechanics part was there in in this particular course.
Yes, sir.
It's more like mathematical. So this particular course will be a bit very easy for someone from link from this mechanical engineering, civil engineering, or the chemical engineering, because a fluid mechanics basic course is there. So these all derivations and everything is very easy for them. That's why slowly.
See that these basics, they were a part of my NEET syllabus. So,
Oh, so no problem
yes,
with the understandings, I think.
yes, sir.
Yes. So these are just force balances, and as for this particular blood vessels, they will be deforming. So in order to consider the deformation of those blood vessels, these standard relations are being developed, because this whatever we study during the NEET and also in the basic fluid mechanics, whatever is being taught during this bachelor's BTech, uh, after the 4 year also 4 year of the BTech, there this flexible boundaries are not being considered. If the wall of the pipe is deforming, so those considerations becomes important in this particular problem that is with this cardiovascular system, right? So that's why this sigma r, sigma theta, somewhere some assumptions are being made in order to get some some particular solution. Like here also you see this sigma r, sigma theta, and then this epsilon r becomes zero, epsilon z becomes zero under some constraint, so that some relations we can get out. So this particular answer to these questions will be like this one is correct or wrong. Just anybody, you can just attempt even if it is wrong, no problem. You can just attempt because these are there in the lectures. So once you will be going through, once you make mistake, then it is more easy to recap them, or like it will be by hearted, right? So the correct answer for this is option D, which is this sigma r by r, sigma r minus sigma theta divided by r equals to 0. And this one is also correct if you just replace this particular word. This was this circumferential. So these are two, these both are same. So what is that? So here if you write radial, then this also becomes correct. So only this option is correct, this one is wrong, because the red was the question that was there. So D is the correct option for the same, right? And then another question is for the thick wall cylindrical tubes, right? For the thick wall cylindrical tubes, the differential the differential equation for radial displacement, and solution for the radial displacement is option A is right. Option A is du by dr plus 1 by r du by dr minus u by r equals to 0. Option B is d2u by dr2 plus 1 by r du by dr minus u by r square equals to 0. Right. Option C is about the solution of the same. U equals to C1R plus C2 by R, and D is U equals to C1R square plus C2 by R square. So which of the following is correct? For the it's actually coming from the computability condition. Like for the thick walled cylindrical tube, uh, uh, you can write compatibility condition, right? So which of the following is true? So as you look at this again, these are important uh, because these equations will be anyway used in few lectures ahead sometimes, and there will be some this bifurcation analysis, and then this pulsatile flow consideration, and that time this terms will be coming up again and again. So this particular answer to this will be that was the second order. If you remember, you started with this calculation of this strain in the radial direction and strain in the circumferential direction. That was the hoop strain. And then this, you had this finally the displacement, second order derivative, and then solution to this under the certain assumptions. The assumptions that you took was this uh, this sigma r was minus p for something. So anyway, these solutions I'm not talking about. I was just telling asked about this general expression for the same. What was the general expression for this displacement vector, right? So now if we see is so which of the following is correct? Question. Which of the following is correct about the blood viscosity? Like what is correct about blood viscosity, right? So what is correct about blood viscosity? Option A is non-Newtonian, yeah, behavior at high shear rate, shear rate. Okay, its viscosity is around 3 to 4 centipoise, right? It is it 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 is viscoelastic. It has viscoelastic behavior. Blood is it is viscoelastic behavior, and then 1% of blood is red blood cells. We also called it erythrocytes. Sites, right? Okay. So anybody just attempt. So another was this about the dimension of the blood vessels. Like there was various things, na aorta, artery, vein, vena cava. So the relative dimension of that. So about that also there will be some questions. This arterial capillary values. So the relative dimension and then its thickness. So the next question that was there, like I think about the diameter, some questions are there in the assignments. So you just solve this question. Until then, I am writing the next one. The question is, okay, this is this. Yes, this is this. Uh, which of the match wait. This thing. C is the correct. You are saying viscoelastic is there, right? Viscoelasticity is right. Then with this can be multiple option. What I am saying this. So non-Newtonian was the incorrect. D is correct. C is correct, right? And then viscosity. So is this correct? Viscosity is 3 to 4. Can we say that this is the exact viscosity, or its viscosity changes under certain conditions?
Sir, its viscosity changes under different
So we
conditions.
cannot say that this is correct. So right, viscoelastic behavior is there because of different constituents like RBC, WBC, and then platelets, and plasma is always anyway water-like, so it's Newtonian. But different conditions will have different viscosity. For example, like sometimes we have heard about like somebody is having this cardiovascular problem, like somebody had heart attack or something. So doctors prescribe them thinners. So what are those thinners? Anybody knows? Like thinners, drugs they give, some medicine that they give in order to reduce the
Aspirin.
yes, reduce the viscosity of the blood. Why so? Because
It's a blood thinner,
yeah.
sir. Aspirin.
So why doctors prescribe those blood thinners? Actually, what is happening at the hematodynamics, like with the flow of the blood. So if the blood will be thin, then
Force increases.
yes. So ease of blood flow increases, and
Yeah,
then
BP increases.
yes, blood pressure increases. Right. So that's why. So everything is related to this. The dynamics of the again the property of the blood and the 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 fluctuation that is happening at the wall of the blood vessel. So like in another condition, I think thrombosis is that condition where this plaque formation happens at the wall of the interior wall of the blood vessel, where there is this reduction in the effective cross sectional area of the blood for the transport of the blood. So because of that, suppose this is the blood vessel. In that situation, this suppose this is the thrombosis. This is this buildup of the triglycerides or fat that we call plaque. Because of that buildup, this happens because of the I think sometimes it's hereditary and sometimes it's like because of the hygiene or the living cycle, like the food habits and everything. Along with the time it happens. So suppose this is the blood vessel, and here what happens? This flow of the blood pattern changes, and because of this also, if this percentage opening of the blood vessel changes, like if this plaque grows, there can be blockage, and if this blockage happens, then the remaining part or the subsequent flow of the blood gets inhibited, and there could be some chance of heart attack. So 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 what doctors do? Doctors, in order to solve this problem, they go for some there was two main uh, solutions to this. Is this angioplasty and angiography? Through angiography they will actually visualize where is the problem, and then through angioplasty they will install some instant kind of thing. They will have some stunt kind of thing. Stunt is a titanium made material, like assistant. It will assist, and it will like stop the subsequent blockage, uh, and flow can happen very easily. So I will be showing some demo video and animations about this. So I think it's time to show that. So let me just open those. So these are some YouTube videos only. So but they will be very helpful for, and they are directly related to the topics that we are discussing. So So let me just open that. Yes, it's here. So this is the first one. Ad is complete. So it's from this Gerald Zedet Educations.
You can feel your heart thudding
So
away.
so you can hear the sound or not? If you can't, then I will be explaining in between. Diksha, you can hear the sound or these visuals are video is visible.
So video is visible, but
Sound
unless you play it, you can't make out.
Every time you put your hand to your chest.
sound you cannot hear
No,
or hear. You can hear.
sound I
But
can't
do
hear
you
it.
have any idea what's
So
really
you
going
can
on in
look
there?
at the
Or
visuals.
what
I will
keeps
be
your heart
explaining
ticking
it
as
in
it should?
between.
Every day, your heart beats about 100,000 times,
Right?
sending 2,000 gallons of blood surging through your body. Although it's no bigger than your
So these
fist,
blue are
your
the
heart has the
deoxygenated
mighty
and red
job
is
of
the
keeping the
oxygenated
blood
blood.
flowing through 60,000 miles of blood vessels that feed your organs
So
and
I will be
tissues.
opening this, then it will be easy. Yes.
Food.
So this
Do you have
transcripts
any
will be there.
idea what's really going on in there, or
Yes.
what keeps your heart ticking as it should? Every day, your heart beats about 100,000 times, sending 2,000 gallons of blood
So around
surging through
2000
your
gallons of
body.
blood is surging through our
Although
body.
it's no bigger than your fist, your heart has the mighty job of keeping the blood flowing through 60,000 miles of blood vessels that feed your organs and tissues.
So
Food, water and oxygen are essential for the existence of human life. Blood transports all these substances through various channels called
it's
blood
like
vessels.
overall
Blood vessels
flow
involves
and this
arteries,
is the pulsatile flow, which is because of this pumping of the
veins,
blood vessel, pumping of the blood, this pulsatile flow veins,
capillaries.
and then these are the capillaries. If we see
To keep the blood
the
flowing throughout
smallest
our body, we have a pumping
bifurcation
system,
of the
and the heart is the pump,
arteries or veins. So these
which is composed of
the
muscle
continuous
that
pumping
pumps
is
blood
happening.
throughout the
So
body,
per minute
beating
around this
approximately
5
72
liters of the
times per
blood is
minute
being
of our
pumped.
lives. The human heart has
And
4
so the
chambers.
4 chambers that
The
again
right
right
atrium,
atrium was this. Again these were explained in the lectures
the
also.
left atrium,
Left atrium,
the right ventricle,
the bigger part where the pumping is actually
and the
happening,
left
and
ventricle.
the left ventricle. Right. So
There are 4 valves in the heart. These valves are
so all the 4
tricuspid valve,
walls, this strike, this actually
mitral
comes
valve,
in the right ventricle.
aortic valve,
Okay, and then this
pulmonic valve.
pulmonic wall, from where the entire
These
deoxygenation
valves are one-way valves.
So
Now,
like this,
you
the
have seen the structure
deoxygenated
of the
blood.
heart. Let us find out how it works.
So overall, the pumping and the
The
flow
blood
is
becomes oxygen-rich by absorbing
continuously
oxygen in
done.
the lungs. The function of the heart starts when oxygenated blood is carried from the lungs to the left atrium
So
of the heart by means of the pulmonary veins.
so
The
pulmonary
left
veins are
atrium
actually acting
relaxes. This blood is pumped into the heart.
and the blood came
When
from
the
the
left
lungs.
atrium contracts, the left ventricle relaxes simultaneously. The left atrium pushes the blood into the left ventricle through the one-way valve. When the left ventricle contracts, the blood is pumped into the aorta, which carries oxygenated blood to
So
the different parts of the body, except the
these are
lungs.
self-explanatory almost. Like during the discussion, this
Oxygenated
pattern has
blood
to be
reaches the
by
different
hearted,
parts of the
like from
body
where the
through the
blood flow
blood
is
vessels
starting
called
and
the
how
arteries.
the
The
blood
arteries
is
gets branched into
actually
capillaries,
leading
which
to
then reaches
entire
to the different organs of
flow
the
of the
body.
blood throughout the body.
The
So
blood then
this
becomes
map has to be by
deoxygenated,
hearted. Like,
and the blood capillaries gets mixed and form thicker blood vessels called the veins. The veins carry
and
deoxygenated
now
blood to the heart.
this
The blood
right part
vessels
of the
that carry deoxygenated blood to
heart
heart
will
are
be the
known as the vena cava.
so vena cava will carry the deoxygenated blood.
The
The heart.
deoxygenated blood from different parts of body enters the upper right chamber of the
So right
heart,
chamber
which
will
is called the
collect
right
the
atrium.
deoxygenated blood
The
and
right
then
atrium
oxygenate
gets
it again.
contracted, allowing the blood to flow into the right ventricle, which contracts with the expansion of the right
So
atrium
this
through
was
the
it
one-way
for this
valve.
particular thing.
The right
So and
ventricle
then there
blood
will be
to the
this
lungs for
overall
oxygenation.
oxygenation
The
and
lungs
deoxygenation
oxygenate the
cycle
blood
happening.
by exchanging of
Okay.
gases and
There was
flows back
another
into the
one I
heart
was
through the
looking at,
pulmonary
this
vein
stunt related, like stunt
and starts the circulatory cycle all over again.
cardiovascular stunt installation. Angioplasty. I was actually looking at it was angioplasty animation. I think this was that, but this is very small one. So this was the blockages that I was talking about. So they will have something like this. So the exact video was what if the blockage is here, so there will be some installation happening. So let me just see where is that video. Radial. We just see. I think this was that. Yes, this was that video. So it's from Nucleus Medical Media. So we are using it for anyway educational purpose. So we can see it, right? Yes.
A coronary angioplasty procedure is also known as percutaneous coronary intervention. The procedure is done on blood vessels called coronary arteries.
Right.
They supply your
So for
heart
the
muscle with
coronary artery,
oxygen.
this particular procedure is being done. So suppose
The
here the
goal
blockage
is to
is there.
restore blood flow if a
These are the
substance
plaques.
called plaque
Plaques.
has significantly narrowed
So
these
how much
vessels.
narrowing of the blood vessel happened, you see?
To begin the procedure, the doctor will numb the skin in your wrist.
Okay.
A
So here
needle
will
will
be
be
the
placed through
anesthesia
your
happening
skin
in
and
order
into
to
your
numb
radial artery.
overall,
Next,
so that
a
you
flexible
will
guide wire
feel
will be
very
passed
less.
through the needle into your artery.
So this needle will be
Then, the
going.
needle will be withdrawn.
Okay.
It will be exchanged for a small, flexible tube called a sheath. This permits access
So
into
this
your
is
artery.
the entire procedure will be
You may
for the
feel pressure when the doctor
angioplasty.
inserts the sheath, but
Right.
you will not feel it moving inside your artery. Next, the guide wire will be advanced up to your heart.
So it will go up to our heart.
A flexible tube,
see.
called a catheter, will be advanced over the wire to your coronary arteries.
So in order to
The
make
progress of
these
the procedure will be
kind of
checked with an
procedures,
X-ray device called a fluoroscope.
so through the
At
fluoroscope,
this point,
they are
your
able to
doctor
see.
will remove the guide wire. Then, the doctor will move the tip of the catheter just inside the coronary artery to be
how
examined.
they are locating.
A special dye will be injected
So
into
a
the
dye is
artery.
injected there.
This allows your
From
doctor
there
to
they can
view it
see
better
that
with the fluoroscope.
this particular region
The
is
dye
having
will
this
make any
blockage.
blockages in the artery
Right.
stand out.
Because that they
If
are
a
this
significant
dye is
blockage
not.
is found, your doctor will insert a guide
So
wire
guide
into the
wire
artery.
went there, and then
A balloon on the tip of the catheter will be moved along the
there
wire
is this
to the
installation.
blockage. When the balloon
So this
inflates,
nucleus
it will
media,
expand the
medical
artery
media
and
video,
improve the blood
we will
flow.
acknowledge them anyway.
You may feel some chest discomfort while this is happening. After this, your doctor will
So
deflate
this
and remove the
particular
balloon.
thing, this is the stent
A
that I
wire
was
mesh
talking
tube
about.
called a stent
So
may be
where
placed in the
the
treated area.
blood
The
vessel got
stent helps
narrowed,
keep the
it will
coronary
actually
artery open.
solve it, that particular reason.
Your doctor will choose the proper size stent, which is compressed over a balloon.
Okay. So
The stent will be moved into the artery over the same guide wire. When the balloon is
Okay.
inflated, the stent will expand and lock
wow,
into
you
place.
see how this
After the balloon catheter is taken out,
expansion of
the
the
stent
stent
will stay in
happened,
place
steady
to
state,
hold the
and it's
artery
now
open.
there. So now the blood can flow.
At the end of the
Perfect.
procedure, the guide wire will be
Guide
removed.
wire is removed, and it is
To
installed.
find out more about coronary artery
Where is that?
angioplasty, talk to your healthcare provider.
Right. So that was the procedure of the angioplasty. I hope this particular lecture gave you some insights about the same. And I think it's 9/6. So meanwhile, I will be taking some of the questions in the next week also. I will be like, though in the next week I cannot discuss about the first week content, but you all are free to ask any questions from the first week content also. And meanwhile, I will be taking some of the questions from the first week content also in the upcoming next weeks. So that was it for today's lecture, and thank you. Any question, if you are free to ask. Hello. Pratiksha, Prem.
No, sir. Not right now.
Okay. Okay. So if there is any, you just have them, and like anyway, every week we will be meeting. I think the same time. Every week, same time, with the different.
Thank you, sir.
Okay. Okay. Thank you. Thank you so much.
Thank you, sir.